I might not be able to read the chat box, so please say something if there's any problem. So what is silicon on insulator? Now, so if you look at this looks pretty similar to a regular transistor, right? You have N plus, and I can tell you that this is the gate, this is the source, this is the drain. And similarly, I have a PMOS, this is the gate, maybe this is the source, this is the drain, right? And definitely then this must be the body, right? And this part is the silicon, right? This whole region, right? The P plus B and this, it is the so-called silicon. And now you might understand why it's called silicon on insulator, because underneath we have the insulator. Usually it is silicon dioxide for the quality control, because it provides better interface and quality. This is why we call it silicon on insulator. You basically build a transistor on top of it, right? After, when it is on insulator, the rest doesn't matter so much. You can still have it on a silicon substrate. That is usually what we have. Why do we want that, right? So I just briefly say why. Because it has less parasitic capacitors, so it's good for RF, radio frequency, microwave application. It means high frequency application. This is SOI, right? It has something less latch-up, so it is radiation hard. What does it mean for radiation hard? If you shoot a particle, you don't do it deliberately, but in our ambient, we have a lot of particle coming from the cosmic radiation from the universe, right? They go through the atmosphere. It can be alpha particle, neutron, they're all high energy. They can screw up the state of the transistor. We won't go into detail, but basically what they do is they generate electron hole pair, and then you will cause some latch-up, or if it is a memory like SRAM, you will cause the flipping of the state. So this is something very important for the military application, right? So like we have many students, they after graduation they join Raytheon or Lockheed Martin. They are all the important vendor for the Department of Defense. They do a lot of this type of product, okay? But we won't go into this in this class. But just know that it doesn't have the bulk leakage, of course, because this bulk is not connected to anywhere. So there's no bulk, right? Again, what is bulk? Bulk is the substrate, right? That we usually call it substrate in the MOSFET, bulk MOSFET, right? And allow through integration of different devices. This is something Global Foundries have been promoting, right? So they particularly Global Foundries has lots of product for different type of special application, and because you have this insulator, which I did not mention, this is also called buried oxide. Okay, they are the same, right? We bury it deep under the silicon that we are interested in, or we call it the active silicon, active because it's using it, and then we bury this oxide underneath it. It provides very good isolation. Then we can put different devices together, bipolar, power, sensor, without affecting each other. So that is the good thing about it. It doesn't have King effect. We talked about King effect last time. We will discuss again this time. Less short channel effect. We did not really discuss what is short channel effect. We will discuss more today. Actually, we did, right? We talked about dipole, but we will discuss deeper, okay? But the problem is that it has a larger self-heating. Also, the fabrication cost is also more expensive, but compared to bulk, in some sense, depends on how you look at it, more complicated. But it has more self-heating. What is self-heating? When I turn on the transistor will heat up. Now, why is that? It has more self-heating because you are isolated by this insulator. And usually insulator has lower thermal conductivity or higher, right? Do you remember we talked about the thermal resistance? Higher thermal resistance, okay? We call it or this is theta T, or let me just call it RTH, right? Thermal resistance, right? It has a very high electrical resistance because it's insulator. At the same time, it has higher thermal resistance. If I remember correctly, it is about 100 times higher than silicon. Also, you trap the heat, then you heat up the device. It's always not good to heat up the device. Okay, so this is just an overview. We will go into them one by one in today's class. Okay.
I have a question.
Yeah.
Are we going to talk a little bit about the fabrication of this kind of structure?
Yes, I will. Not the structure, but we talk about the fabrication of a SOI wafer. That's it. Because then for the fabrication, it's just very similar to about silicon. The fabrication step.
Well, okay, so how do you then deposit? Because the silicon layer that's on top of the oxide is very thin. So I presume you do.
So I will talk about how you form the SOI, meaning that we will talk about how we form this epitaxial layer. But and then the fabrication of transistor is similar to the bulk afterwards.
Okay.
Yeah, I will show you. Yeah. Okay, so the first thing I want to talk about is the latch up. So what is latch up? Let's look at this. Here, what I'm showing you is the bulk, right? The what we usually have, 65 nanometer, 45 nanometer, 22 nanometer, most of 28 nanometer. So again, what do we have here? Here we have a transistor, right? I have the gate, I have the source, I have the drain, and this is PMOS, right? So it is inside N well and N well because a PNP that form a transistor, right? But this N well I need to bias it, right? So this is the body of the PMOS. In the same wafer, this is a continuous silicon. We also have the NMOS, right? This is just showing an example, and this is like an inverter. You have gate here, maybe this is the drain, this is the source, and again, we need to bias the substrate to a certain voltage through this P plus because this is the P substrate. So we have this, we bias this to 0 volt, for example, right? So for those who are familiar with circuits, this is something like this. This is the, let me just use circle to represent PMOS, right? So this is like this. Okay, so this is on the top is the VDD, right? So that's why you see the source here. This is the source and the substrate, a bias to VDD. And then you have the gate, which is the input. Although it's not connected here, let's assume they're connected, so it becomes a inverter, right? On the bottom, you have this VSS, which is the ground. Let me just write it as VSS, right? And then you have this substrate connected to the VSS. At the same time, the source connected to VSS. Here is not shown, right? We should connect these two together. Then it becomes the output of an inverter, right? So in your assignment 1, you are doing a layout of ring oscillator, and what you are actually doing is 3 copies of this part in the real silicon, right? But now we are only talking about the inverter. So this is drain, this is the gate. Okay. Now, this is the problem. We have this N well bias to N plus. So this point is really 5 volts, for example. But your N well actually is resistive. We try to make it conductive, that it cannot be super conductive just because we cannot apply very high dopant, because that's not desirable for many transistor performance. So from this part to here, it's just like that you have a resistor. Similarly, for VSS, this is ground, but again, it's not super conductive. So here you have another effective resistor. This just like the King effect I explained earlier, right? You have a resistor. So if there is any current, then you might make, for example, let's say this is 5 volts. This might become 4.9 volts. Right? Here is 0 volt, and at this point it might become 0.1 volt. Okay, so first of all, you cannot get equipotential if there is any current flowing. Okay, why there's current flowing we discuss later, but assume I have some tiny current flowing. Now then at the same time, you find that I have the PNP, right? This is P, this is N, and this is P. Let me make sure that the student can come in, okay? I don't see anyone is in the waiting room. Okay. Okay then. Yeah. So we have a PNP, right? So what is PNP? So we many of us did not study bipolar transistor, so it's good to take this opportunity to learn a little bit. We don't need to learn too deep. I don't expect to test you in the exam, but it will be good because when you're doing transistor, PNP is always there. So this is another type of transistor. It is just like this. You have N plus, you have a P region, and then a N plus region, right? So I call this collector, this is emitter, and this is the base. Now, collector, actually, we do not put N plus. We will try to use N and then eventually N plus, but we don't go to this type of details. The only thing I want to tell you that this forms a transistor called PNP transistor, and its symbol is just like this. This is emitter, this is base, and this is the collector. And you have current called IC going in. This is very similar to the concept of an NMOS. You have the gate, you have the source, and you have the drain on top. And then you have ID going down. And you know that in NMOS, you turn it on by making VGS larger than VTH, right? Then it is on. Here you make VBE larger than a certain voltage. Let's just call it VBE on. Okay, because this is a diode, so it goes up exponentially. You just take it for granted. Again, you need to be larger than a certain bias to have significant current going from collector to emitter. Just like you need to have the gate voltage larger than VTH to have significant current going from the drain to the source. This is called NPN diode. So all you need to know is that if I have VBE larger than certain voltage, then I'm going to have a lot of current going from collector to emitter. So from this point of view, let me go to this PNP. You have NPN. This is N, this is P, this is N. And what it's saying is that if this point and this point, this is the base, right? If you base on what I'm drawing there, this is the base, this is the emitter, this is the collector. If it is confusing, then you just think as NMOS. This is the gate, this is source, this is the drain. If this part is larger than this part, larger than the VBE on, then I will have a lot of current going through here. I turn on this, what we call the parasitic PMOS. Our goal is to make parasitic NPN. Our goal is to make NMOS, but because of this structure, inevitably, we will get a parasitic transistor. In normal case, think about that. If no current is flowing, this is 0, this is 0, VBE is 0. So even you have a parasitic NPN, no problem. There's no current, right, to the first order. But if there's some current, you cause a potential drop across this R substrate. This may be 0.7 volt, this is 0 volt, then you drain a lot of current. Okay, that is the first thing. Any questions? If no, let's also learn its counterpart, which is P and P. So here you have the emitter here, base, collector. So it is something like this, right? The arrow is different. I don't expect you to memorize it, but I do hope that am I right? This is emitter. Yeah, I just call this IC. Again, this is very similar to a PMOS GSD, that you have the right ID going from high potential to low potential, right? Again, if in the NMOS, if VSG is larger than VTH, right? VSG larger than the absolute value because they are negative. So now I play with absolute value. You just plug in, you will find that is correct. Point is that G is much lower than S. Then I have a lot of current. Same here. If the B is much smaller than E, I also have a lot of current, right? So that is the same for this NPN. Now, because of this resistive drop, this point might not be at 5 volts, but this source is connected to 5 volts. So as a result, I might turn on this PNP. Okay, so if you try to trace the circuit, you will find that I actually have a circuit network like this. Between this VDD and source, even the transistor are not turned on, I have this parasitic circuit. Now, when there is no current going on, this point is VDD, right? When there's no circuit. So let me write it. Maybe this was VDD, and this is 0. When there's no current, right? Or we call this VSS. So if this is VSS, this is VSS, fine. This is off. This VDD, this is VDD. Again, this is off because it's PNP, right? So nothing happened. That is what we want. But if due to any reason, like impact ionization or radiation effect, they generate some electron hole pair, they cause some substrate leakage, then I might have current going down. Now, when this current go down, it will becomes the current to the base. Or in a simpler way, we can say this VDD may becomes, instead of 5 volt, let's say this is 5 volt, it becomes 4.2 volts. And then this one will turn on. Once this turn on, I have lots of current going down. Then if I have lots of current going down, this will become maybe 0.8 volt, right? Because I have lots of current. Then this turn on also. Once this turn on, I have even more current going down. Then this potential drop more. And then you have this positive feedback. And eventually this becomes conductive. Then you short the VDD to ground. And you can heat up the transistor or just damage the die. And that is called latch-up. So let me summarize what you need to know from this slide. It will be really useful if from now on, if you have not learned that before, to understand there's something called PNP and NPN transistor, bipolar transistor, that similar to NMOS and PMOS, and understand their turn on, turn off mechanism. It will be useful to you. That is first thing. Second thing is when you put the NMOS and PMOS together, particularly in an inverter setup, which is just everywhere in our digital circuit, because all our digital circuit are designed with pull up network and pull down network, right? Then this parasitic circuit can be triggered due to some tiny leakage current. It might be very small at the beginning, but then it got amplified. Once it amplified, this will go up higher, then this will turn on and amplify more. Eventually it get positive feedback, and then the whole thing just conduct and you lose all your stuff, right? You will just damage your chip, and this is called latch-up. So here involve a lot of concept. Do you have any questions?
So how do you avoid this issue then? If maybe it's advantageous to manufacture in this P substrate.
Yeah, very good, right? How do you avoid this issue? Then there are a few things. First, if I can make R well and R sub very conductive, it means reduce their resistance, then even I have some current, the potential drop won't be large. Then I won't be able to turn it on easily. Second thing is, this is the active device, right? In real application, we want it to have a high gain. But here we will try to reduce its gain. You can use many different methods, right? For example, you can reduce the carrier lifetime by, probably people don't do that, but for some special circuit, you can induce some, let's say, some defect center so that you kill all the electron and hole generator, let them recombine. Then you have a very low gain, what we call the beta. Right? We did not go into the detail, but later we talk about beta a little bit. The gain of the transistor. You reduce the gain, then even you have current going, then this won't be that large. And what else? Then I can also make them very far apart. So remember the design rule. Some of you already doing the layout and had problem with the design rule. They actually mandate you that you cannot put this contact or this to be very close to end well. They due to certain reason, and one reason is to avoid the latch up. Think about that. If this is really long, then you have some resistor, then you won't have this type of positive feedback easily. That can avoid that. Do I answer your question?
Yeah. Another question I have is, what happens at cryogenic temperatures? Do you actually run into an issue where the two parasitic resistances go up? Is that the case?
So I can hear here. Do you say at cryogenic temperature, this two resistance becomes much larger, so the chance will be larger?
Yeah.
Exactly. Yeah. But on the other hand, the gain of this transistor can be lower. So I don't have a definite answer. But yes, latch up is expected to be more serious at cryogenic temperature.
Okay.
Yeah, good point. Yeah, so he can associate what we learned last time, the king effect to here, because of the carrier freeze out.
I think the published data so far hasn't suggested a good bipolar device operation at cryogenic temperatures in the CMOS process. I don't know if you had some comment on that.
You say they don't have a good bipolar transistor?
Yes.
Okay, I don't have comment. But however, remember this is a parasitic one. True that if you really go to you try to design a high gain transistor, the problem is I did not tell you all the details. In reality, we want to have a nicely doped collector next to P to avoid the so-called early effect. It's just like the channel length modulation in transistor in NMOS. So when it is nicely doped, you might got freeze out. So yes, actually, there's a group I forgot from University Georgia Tech or University of Florida. I forgot the Chrysler's team. I forgot his name. Yeah, they spend when no people care about cryogenic, they spend many years in late 90s to early 2000 to work on this heterojunction bipolar transistor and their modeling. If you are interested, let me know. I can send you their website or paper. But yeah, so it is pretty profound. I don't have all the information, but you are right. We need to consider many things. Yeah. Okay, then how can we prevent latch up? I saved the last part here. Use SOI. If you replace this whole part by insulator, what do you get? No latch up because there will be no leakage current. And this is the SOI. Is this okay? Any questions? Right, so that is one of the main thing of using SOI. So in the past, SOI is very popular when we talk about space application, because you are not going to induce any electron hole pair to screw up the circuit. Okay, then let's go ahead